Good afternoon, everybody. I hope that you are starting to get the hang of what equilibrium means and the equilibrium constant. So today we're going to focus on K. That's going to tell us a little bit about the shift of the equation, tying in a little bit with Le Chatelier's. Remember that we can only predict, so we are predicting that the equilibrium, the tendency of the reaction to occur, not the speed. We cannot tell the speed of the reaction. We'll keep that for chapter 12. What is the concentration at equilibrium and the equilibrium position achieved from a given set of conditions? Now, as we go through what K is, we need to be reminded that K is our equilibrium constant, which is the concentration of our products over the concentration of our reactants. So keep that in mind as we are working through this podcast here. So if I am given a balanced equation and I see that K is larger than 1, then the first thing that I can figure out is that at equilibrium, the reaction to get to equilibrium is going to have to shift to the right. Now, if you think about that, if K is greater than 1, the reaction is just automatically going to shift to the right. It's going to produce more product than reactant. So if K is really, really large, that should make sense to you that you have more product than reactant for that value to increase. Now, some terms that you might see is that it will often say K is in favor, is a lovely word that they like to use for equilibrium, is in favor of the products. And all that means is that the reaction is shifting to the right. It lays in the direction of the products. And then conversely, on the other side, if K is very, very small, that means that the reaction at equilibrium, to attain equilibrium, that the equilibrium is going to lie to the left. So opposite of what we just said, and instead of favor of the products, K is going to be in favor of the reactants. And again, all that word means is which way is the shift going to tend to go. Now, if we take a look at both K in a very large K and a very small K, a very large K, that the reaction is going to shift so far to the right that the reaction almost always goes to completion if it's really large, okay? And so that means that's something that completion, that obviously if you're making some sort of product and you have all these raw materials, you want everything to be used and completely react. That's saving you money. If K is really, really small, the reaction might not occur at all. So if you know you're still going to use those reactants, then that's when you need to study, do I need to change the temperature and pressure and surface area and all those other things. So the size of the K and the time required are not related. Size of K and time. We cannot relate equilibrium and speed or kinetics at the same time. We know that the time required to reach equilibrium, one thing that it does depend upon is the activation energy that we talked about in chapter 12. So how much energy is needed there to break those bonds and reform them to make your products. And the size of K is determined by the energy factors between the products involve entropy. Now we haven't talked about entropy yet, and that just simply means organization. So how organized are the reactants and the products to be able to get through the reaction? Okay, now reaction quotient isn't going to look any different than anything that we have already done. But reaction quotient is something that we're going to use to compare to K so we can figure out the shift. So I just told you that our equilibrium expression is equal to the concentration of the products over the reactants. And you are going to see that Q is the same thing. So it's the concentration of our products over the concentration of our reactants. We will get our value and then compare to K to determine the shift. And we'll be doing some problems to figure this out. Well, if I do this and I have all my products and reactants and I figure out what Q is and they are equal, And yes, hopefully you are saying, oh, I must be at equilibrium. So there isn't going to be any shift in this equation. Now, if I think about that Q is too big, so Q is really large, okay? You can look at the little alligator like you used to do in elementary, that if Q is too large, my alligator is eating Q, so it's going to say the same thing, that I need to shift to the left, okay, because I have too much product. So it's going to shift to the left to reach equilibrium. If that's our goal, is to reach equilibrium, if Q is bigger than K, I'm going to have to shift left. What this says is that the concentration of the products is too large, and I got to do something to alter my reaction to shift it left. And then obviously the opposite, I can focus on my little alligator here, that if you put Q first, Q is less than K, my alligator is eating to the right, and the same thing to achieve equilibrium. Now this is to achieve the equilibrium, it's going to have to shift to the right. All right, and so if you think about that Q is too small, then I don't have enough reactants to push it. And so I'm going to have to shift, or I don't have enough products to push it. So I have to make some more and shift it to the right. And what those stresses might be is what we learned in Le Chatelier's principle. Do I have to change the amount of energy in the system by adding heat or removing heat? Do I have to change the volume? Do I have to change the pressure? Like, what is the stress that's going to be there to cause the shift to move in the direction that I need it to reach equilibrium? Okay, so just a little bit about Q and K, and we will put that in action when we work through some book problems. Have a great day.